So precipitate has more to do with the fact that some ions attract each other better than others. Right? So if I take like Na2SO4 as an ionic compound that combines a metal and a group of nonmetals, I can recognize that really that consists of two Na pluses and an SO4 2 minus. Right? That repeating unit has no charge overall, but the individual parts of it are charged. So if I take that as a solid and I introduce it to water, and I dissolve it, if I see the solid mixing in with the water and becoming a homogeneous mixture, and I don't see the solid particles anymore sitting on the bottom and they all mix in and totally dissolve, what happens is I get the sodium ions and the sulfate ions separate from one another. And that substance is fairly soluble in water. If I put it in water, the ions separate. And the reason for that is because the sodium doesn't really form that strong of an attraction with the SO4. Some ions just form better attractions. The attractions between the ions are based on the quantity of charge involved, more charge, stronger attraction, and how effectively they can pack into a solid. Right, so when we think about a solid, we've got rows and columns of these things. Depending on the sizes, if they're all the same size, it's hard to pack them in without creating some gaps in here. But if some of them are larger and the other ones are smaller, the smaller ones can fit like right in those gaps sometimes. And that allows the charges to get even closer together. So the effectiveness of the packing of the charges and the quantity of charge involved determines how strong the ions are attracted to one another in the solid form. And that determines whether you get a precipitate or not. So if I have these in the solid form and they're plus minus, plus minus, plus minus, and they're not really attracted that well, I put it in water, they're going to separate, and the water molecule is going to form ion-dipole attractions and surround them and keep them separated. If they form really nice attractions, though, even if they were to separate, once in a while as they're moving around solution, their charges would attract and they would come back to form a solid. So some solids just are not soluble, not nearly as soluble. It depends on the specific ions involved and how strongly they can attract one another and how effectively they can pack into a solid where they can really maximize those attractions. So real quick, in a precipitation reaction, that usually occurs if I've already got aqueous solutions. So if I've already got Na2SO4 dissolved in water, and I add something like lead chloride that's also aqueous, now I've got a lot of ions. So what we said was the sodium and the sulfate don't attract too well. And if this is already aqueous, that implies that the lead and the chlorides are also already separated from one another. Aqueous means everything's dissolved and the ions are already separated. But if I introduce those two solutions together, if two of the ions maybe have a really strong quantity of charge or they can pack together in a very effective way, then if I mix all of that together, I might form a precipitate because maybe the lead and the sulfate with their extra quantities of charge will form a solid. And the sodium and the chloride will remain aqueous. And so what that means is the lead and the sulfate as a solid will form these effectively packed chunks of solid where the ions come together and form strong attractions, and the other ions that don't form attractions that are strong will just stay separated, surrounded by water molecules. Do you have a question, Helen? Yeah, that's true. Strong acid forms weak attractions. The difference, though, is in a strong acid, the attractions that are weak are covalent bonds, and so they break, and that acid donates a proton to the water. Here, the attractions we're talking about are ionic bonds. Right? So, in order to break up a solid in an ionic compound, I don't have to actually break any covalent bonds. I don't have to change in any way how the electrons are shared. In an ionic compound, I just have two groups or two atoms that already have opposite charges and are not really associated with each other in any way other than the fact that those charges attract. So the solubility of ions and the likelihood of ions precipitating only has to do with how effective are the attractions. It doesn't have anything to do with octet rules or covalent bonds or shared electrons. It only has to do with, are these charges going to be more stable if they're separated and surrounded by waters, or are they going to be more stable if they come together and stack up and form a solid? And so that's what we're talking about. If we see a precipitation, if we see that when we add two aqueous solutions, we get a solid forming, it's because some of those ions just happen to form especially good attractions and the water is not able to keep them apart. Right, in the water, you've got the water molecules moving around. There's a fair amount of translational motion. Things are flying around and sliding past one another. All that motion and the collisions that result from that motion make it hard for particles to stick together. If you raise the temperature, you have even more motion, even stronger collisions. Those collisions make it hard for things to stay together. So that's why there's a tendency for the ions to stay separated when they're in solution, because the water molecules can surround them and keep them apart, and the motions keep them from forming strong attractions that allow them to come together. But if they form really strong attractions because of the quantity of charge involved or the way that they pack together, then you might see a precipitate form in solution, or you may have a solid that doesn't really even dissolve at all to begin with because of the ability of the tractions to keep it together and not get separated even with all those collisions.